All right, friends, let's keep this going and let's talk about 8.3 rational functions and their graphs. So, just a second ago, we talked about reciprocal functions, and rational functions look very similar to those reciprocal functions. So, that's why we do these two sections together. So, we're going to look at what are the properties of rational functions and then how do we graph them. So a rational function is a function that you can write in the form f of x equals p of x over q of x. And p of x and q of x are polynomials. So in simpler terms, a rational function is where you have a polynomial over another polynomial. And just like we saw with reciprocal functions, the domain of a rational function is going to be all real numbers or you can use that boldface R that we're used to, except where the denominator equals 0. So whatever's going to make that denominator go to 0, that is our restriction. And like I said, we saw that with reciprocal functions that we just got done talking about. So for example, if you have x minus 2 over x plus 3, your domain would be all real numbers except when x equals negative 3. Okay. So there are three major types of rational functions that we're going to look at today. And you can see down here at the bottom all three of them, and they look a little funny, I know, but we're going to dissect them and look at them very carefully. So the first type of rational function is called a continuous graph because there are no jumps, no breaks, or no holes in the graph. I could use whatever x value I want here, and I'm going to prove this to you. The reason I don't have a restriction here, so my domain would be all real numbers, is because no real number is going to make that denominator go to 0. So a quick way to find your restriction is to set your denominator equal to 0 and solve. So you would have x squared equals negative 1. When you take the square root of both sides, x is equal to plus or minus I. Well, again, there's no real number that is going to make that denominator go to 0. So that's why our domain is just all real numbers. And the shortcut to recognizing a continuous function is when you have that x squared plus some value. Anytime you have that x squared plus a value in your denominator, it's a continuous function. Now, what does it mean to be discontinuous? You guessed it. There are jumps, there are breaks, and or there are holes. So, what does it mean, or what does it look like per se, if we have some discontinuity? Well, in this first example right here, you notice that your polynomials are in factored form, and that's really important because when we're in factored form, we can see here a lot of things. The first thing we can see is our domain would be all real numbers except when x is equal to negative 2. But then you notice that x plus 2 on the bottom cancels out with the x plus 2 on the top. So that's why this function graph down here below looks like the line x plus 3, because that's all I'm left with. I'm just left with x plus 3 after I canceled out the x plus 2's. But that still presents a restriction because we always want to state our restrictions before we cancel. So we said the domain is all real numbers except at -2. So it is acting like a continuous function, except when x is -2, there's a hole at the graph. And then I just keep on graphing like I normally would. So the rule of thumb here, if a factor cancels, there is a hole at the restriction. So if the factor cancels, there is a hole at the restriction. So that leads me to this next example over here. This is another form of a discontinuous function. But you notice here, once you state your domain, which we always do first, domain would be all real numbers except when x equals 2. Okay? But you notice here that the x minus 2 cannot cancel out with the factor x plus 4. Okay? That can't happen. They have to be the exact same if they were going to cancel. And they do not cancel. So what does this mean? This means instead of a hole at x equals 2, you have a vertical asymptote at x equals 2. And we just got done talking about vertical asymptotes in 8.2. Remember, it's like that invisible dog fence, right? You can get insanely close, but you're never going to cross it. It is its own boundary. So, let's recap. If the factor does not cancel, the restriction is a vertical asymptote. If the factor does not cancel, that restriction that we stated in our domain would be an asymptote. So again, let's recap. I just want to emphasize this because I really want you all with me and I want you paying attention. Eric, turn around. Stop talking to Cody and Zach. Vinny, stop talking to Case. I see you. Okay? So, say it with me if you need to. If it cancels, it's a hole. If the factor does not cancel, we have a vertical asymptote. Now on this next slide, I want to show you those two functions that we just looked at. I want to show you what they look like on your calculator. Because as we just saw with this first one, there was a hole at -2, right? But when I graph it on my calculator, if I type this function in just like I have it on my calculator, okay, my calculator does not show on the graph that there's supposed to be a hole in the graph at -2. Where it does show it, though, is right here in the table. Okay? Your calculator is sadly not fancy enough to graph the physical hole in the graph, but it does tell you on the table, oh, at -2, there is a hole there. Same thing with it when it comes to asymptotes, okay? On this equation here, we notice that our domain would be all real except 2, and that doesn't cancel with any of the factors on top because they don't match. So what's happening at 2? You have this vertical asymptote, but again, your calculator doesn't necessarily graph that dotted line. The graph makes it approach that vertical asymptote, and you can see how it's taking shape. Again, it will show you on the table that you have an error at that restriction, but you have to see, oh yeah, it's an asymptote at that point. So let's go ahead and fill out some more notes and let's put this into practice. Vertical asymptotes occur. Let's see if you can paraphrase here. Vertical asymptotes occur at what? At restrictions that do not cancel. So what does that mean for holes? Holes occur at restrictions that do cancel. Okay. So on this first question, it says, what are the vertical asymptotes of the graph? What are the holes of the graph? So the first thing we're going to do is state our domain. So our domain would be all real numbers except when x equals 2 and when x equals 3. Now, do we see any of the factors on the bottom cancel out with any factors on the top? No. So what would we say here? We have no vertical asymptotes. We would say we have no holes. Sorry, friends. We would have no holes here because they don't cancel out. But we have two vertical asymptotes when x equals 2 and when x equals 3. So when I graph this, you would see the first thing would be that vertical asymptote at 2, and then you would have another one at 3. And if you want to take a second and see what that looks like, you can totally graph it on your calculator. It's actually pretty interesting. Okay. Let's look down here at the bottom. If you want to try these on your own, you're feeling pretty confident, go right ahead. If you want to follow along with me, let's go. On A, again, we're already in factored form, so let's look at the domain. It would be all real numbers except when x equals 1 and negative 3. Do any of those factors on the bottom cancel out with the factors on the top? No. So we have no holes, but we have two vertical asymptotes when x equals 1 and when x equals negative 3. On B, again, they already factored it for us. That was nice of them. So we can go ahead and state the domain. That would be all real numbers except when x equals positive 2 or negative 3. Now, do any of the factors on the bottom cancel out with any of the factors on the top? Yes, they sure do. That x minus 2 and that x minus 2, they cancel each other out. So we would say we have a hole when x equals 2, but we have a vertical asymptote when x equals negative 3. So we had both on that one. Let's look at C. On C, you have x squared minus 1 over x plus 1. So what you're going to have to do here, they weren't nice to us on this one. We have to factor this first. Now we can see what's happening. My domain is all real numbers except when x equals negative 1. Now the question is, do the factors on the bottom cancel out with any of the factors on the top? And they do. So what's happening at my one restriction here? I have a hole when x equals negative 1. I don't have any other factors on the bottom, so I don't have any vertical asymptotes. Okay. If you need to, take a second, pause, reflect on these answers, And when you're ready to move on, just go ahead and press play. So the next thing we need to talk about, once we've identified whether our restriction is a hole versus an asymptote, we need to talk about how do you find the x and y intercepts. Now, I have hounded you all on making sure that you know how to find the x and y intercept, and those same kind of principles apply here when we're dealing with rational functions. So to find the x-intercept of a rational function, you set the numerator equal to 0 and you solve for x. That's probably the only new piece of information here. To find the x-intercept, you set the numerator equal to 0 and you solve. If you want to find the y-intercept, you do what you do every other time I've asked you to find the y-intercept. You plug in 0 for x and you solve for y. Okay? Big important part right here. I wanted to star it. I'm underlining it, highlighting it. Oh my goodness, you got to know this. You have to identify these intercepts after you cancel. Okay? So once you're in factored form and you've done your restrictions, you've told me whether they're vertical asymptotes or whether they're holes, the next thing is to cancel them out and find your x and y intercept. So I'm going to do a mini example here just to get you warmed up before we move on. So it says, what are the x and y intercepts for the following function? Well, the first thing I want to talk about is that domain restriction. All real numbers except when x equals 2. Now, does the factor on the bottom cancel out with anything on the top? No. So here, I'm just going to go right ahead and find my x and y intercept. To find the x-intercept, you set the numerator, and only the numerator, equal to 0, and you solve. So by the zero product property, we have x minus 3 equals 0 and x plus 1 equals 0. So my x-intercepts would occur at 3, 0 and negative 1, 0. To find my y-intercept, all I have to do is wherever I see an x, I'm going to plug in 0. So I would have 0 minus 3 times 0 plus 1 over 0 minus 2. So that gives me negative 3 times positive 1 over negative 2. So that gives me 3 over 2. So my y-intercept would be 0, comma, 3 halves. Am I going to take points off if you don't write it in the right form? Everybody, yes, I will take the points off. You know how to write an x and y intercept. Okay, so the x-intercept, you set the numerator equal to 0 and solve. Y-intercept, plug in 0, simplify, and solve. So on this next slide, we are going to put everything together. Everything that we have done thus far is going to come down to this slide. Okay? The problems here say identify the holes, the zeros, the vertical asymptotes, the x-intercepts, and the y-intercepts. Okay? Vocab, aren't zeros the same as x-intercepts? Yes! Going back to last module. Okay? I just repeated that twice. See if you caught it. On A, let's go ahead and get rolling here. The first thing you notice is this is a rational function. You have a polynomial over another polynomial. But that bottom is not factored. So the first thing you need to do is see if any of the polynomials can factor, in which they do. So I'm going to rewrite this as x plus 3 over x minus 3 times x minus 1. From here, let's talk about the domain. I would say I have all real numbers except when x equals 3 and 1. I should probably say 1 and 3, but for the sake of time, here we go. From here, I need you to ask yourself, do any of the factors on the bottom cancel out with any on the top? No, none of them cancel. So what do we say here? We have no holes, but we have two vertical asymptotes. We have it at x equals 1, and we have it at x equals 3. Last thing, find the x and y intercept. To find the x-intercept, we set the numerator equal to 0. So that would be at -3, 0. And for my y-intercept, I plug in 0 wherever I see an x. So that's 0 plus 3 over 0 minus 3 times 0 minus 1. That gives me 3 over -3 times -1. Which gives me 1. So my y-intercept would be 0, 1. Lots of parts here, but it's not too terrible, okay? Especially because we already know how to recognize whether we have holes or asymptotes. So really the only thing new to practice here on this slide is practicing finding that x and y intercept, okay? On B, let's talk about B. Ooh, what do we notice about B? Oh, look right here in the denominator. It's a continuous function. So let's see if we can factor this, and then we'll talk about our domain in just a second. Can I factor x squared plus 1? I cannot, because that is, I know what y'all are thinking. You would think x squared minus 1, because that's the difference of two squares. That would factor to x plus 1, x minus 1. But x squared plus 1 does not factor. So I'm in my simplest form right now, and we know that that's a continuous function. So do I have any restrictions? Nope. No restrictions. My domain would be all real numbers. So what would I say about the holes? No holes. And no vertical asymptotes, because this is a continuous function. I have no restrictions. I have no breaks. I have no jumps. So I have no holes and no asymptotes. So here we go. Let's go ahead and find the x-intercept. Set the numerator equal to 0. And I would have 5, 0 for my x-intercept. For my y-intercept, plug in 0 wherever you see x. So that would be -5 over 1. So that would give me 0, -5. I love those continuous ones because they are super easy and they just go really quickly. Okay. If you can, see if you can try to do C on your own. If you're still feeling kind of hesitant, you can go ahead and watch me work this one out. So again, on C, we notice here that the polynomial is not factored, and we need to factor it. So that would go to x minus 4 times x plus 1 over x minus 4. And we're going to state our domain restrictions. This would be all real numbers except when x equals what? X equals 4. Now here, when I go to talk about the difference between a hole and an asymptote, again, does anything in the denominator cancel out with a factor in the numerator? Yes. So what's happening at 4? We have a hole at x equals 4. Now, that leaves me with x plus 1 on top. If you want to put over 1, that's totally fine. But now, when I go to find the x-intercept, I only have one numerator to set equal. I only have that x plus 1 to set equal to 0. So that would be at -1, 0. For my y-intercept, again, I'm plugging in 0 to my completely reduced form. Okay? You find the x and y intercepts after you cancel, so I'm just working with my simplified form here. So to find the y-intercept, plug in 0 for x, and you get out 1. So when do you find the x and y-intercept? After you cancel, and I showed that in C. If you need a second to recap, please feel free to pause the video again at any time. If you're ready to move on, I'm going to go ahead and move on as well. So here on this next slide, I really, wherever you're at, I want you to go ahead and hit pause and see if you can go ahead and try these on your own, okay? Give these a shot, see if you can handle it. They are a little bit challenging. They're going to push you to think, but that's exactly what I want to happen here. So if you can, pause it and then hit play when you're ready to check your answer. So here on this first one, we have to factor first. I'm going to state my domain restrictions. All real numbers except when x equals 4 and negative 4. Now, do any of these cancel on the top? No, they don't. So what does that mean? That means I have vertical asymptotes at x equals negative 4 and 4. That also means no holes. So here on this one, when I talk about the x-intercept, we notice that the x-intercept, the numerator, equal to 0, but does 1 ever equal 0? No, that never happens. That doesn't mathematically make sense. So what would we say here for the x-intercept? There isn't one. I don't have one. It doesn't cross the x-axis, okay? So here with the x-intercept, we would say none. For the y-intercept, remember, plug in 0 for x, and we would get 0, negative 1 over 16. Where did I get that from? I plugged in a 0 for my x, and I simplified. This is really important. Okay. All right, on this next function, let's see if we can go ahead and factor it. The top factors, and so we're going to change that to say x minus 1 times x plus 1 over x squared plus 3. I cannot factor that denominator, and you should also notice that this is a continuous function. So the domain is all real numbers. No vertical asymptotes and no holes. So when I go to find the x-intercept, I set my numerator equal to 0 because I don't have anything that canceled here. So I would have 1, 0 and negative 1, 0. For my y-intercept, you plug in 0 wherever you see an x. So that would be negative 1 times positive 1 over 3. That gives me negative 1/3. Y'all, my board is doing that thing where it like blacks out like while I'm in the middle of writing, so I am so sorry. All right, let's try this last one. I need to factor. And I'm going to state my domain restrictions. All real numbers except when x equals negative 1 and negative 2. Now, before I go carried away with the x and y-intercept, I need to talk about the holes versus the asymptotes. Do any of my factors on the bottom cancel out with a factor on the top? Yes. Those x plus 1s cancel. So what does that mean? I have a hole when x equals negative 1, but I have a vertical asymptote when x equals negative 2. So now let's talk about this. Simplifies to 1 over x plus 2. So I'm going to use this simplified form to answer the questions about my x-intercept and my y-intercept. X-intercept, set the numerator equal to 0. Does 1 ever equal 0? No, we just talked about this. So what does that mean? I have no x-intercept. To find my y-intercept, plug in 0 for x, and you get 1/2. If you're good, go ahead and move on. If you're not, pause. Take a second. Digest this. Last 2 slides here, putting it all together. So what is the graph of this function, okay? Now, I'm not going to make you graph these by hand. So if you want to graph these on your calculator, you totally can. But I do still want to see some work of you working through the process here. So first thing, let's go ahead and factor. So my domain restrictions, I would have all real numbers except when x equals -2 and +2. So from here, let's talk about, do we have a hole? Nope. Why do I not have a hole? Nothing. Down here cancels. But I have 2 vertical asymptotes. I have a vertical asymptote at -2 and I have a vertical asymptote at +2. So I'm going to go ahead and plot those vertical asymptotes. At -2 and +2. So nothing cancels, unfortunately. So let's go ahead and find our x and y-intercept. X-intercept would be -4, 0 and 3, 0. So I can plot those. Okay, and now let's find the y-intercept. Plug in 0 for x. This one's going to be a doozy. You got 4 times -3 over 2 times -2. That gives you -12 over -4. So that would be 0, 3. Okay. So from here, if I wanted to be cruel, I totally could. Don't give me that look, Vinny. I could totally be cruel here and make you graph this by hand, because what would we do to get more points on our graph? Just like we did earlier in this last module, I would plug in other points for x. Like I could plug in -1, I could plug in +1, I could plug in 2, 3, 4, 5, 6. I could plug in -3, -4, -5, etc. I could plug those values in and figure out what I get out, just like I did for the x or for the y-intercept. Okay? But I am not that cruel, so you can go ahead and get your calculator. So on your calculator, make sure your plot's off from this past test. And when you type this in, I would definitely use the fancy fraction, the alpha y equals, because we want to make sure we have that whole fraction in there. If you don't have the fancy fraction, you're just going to have to use extra parentheses when you're typing this in. To get back to a normal window, make sure you hit zoom 6. Otherwise, you won't be able to see it very nicely. So you can see this graph, based off of those 2 vertical asymptotes, you create kind of a little mini parabola there in the middle. Okay? Oh, also, just be mindful, you might want to change your table back to auto. So go to second window and change that independent back to auto, so it'll generate it for you. So here on your table, you can get some more points. Like at -1, you have 4. Whoops. At 1, you have 10/3, so a little bit past 3. It's not exactly a parabola, but you can kind of see it there. And then from here on the other side, at -3, we have -1 right there. And you can plot as many points or as little points as you need to. Okay. So again, graphing, that's just going to happen on your calculator. I'm not going to be that mean. Okay. Perfect. If you want to try this one on your own, I encourage you to. Okay, this is the last problem that we're going to look at here in 8.3, and then we're done for the day. So again here, the first thing I'm going to do is factor, state my domain. This would be all real numbers except when x equals 5 and 1. Now what do we know about 5 and 1? They are not wholes, unfortunately. They are both vertical asymptotes. So x equals 1 and x equals 5. So we can go ahead and plot those. So now I can find the x-intercept because nothing cancels here. So I'd be at -3, 0. And the y-intercept, I just plug in 0 for x. And we get 3/5. It's going to be really hard to graph 3/5, but we can do it. All right, so on your calculator, go back to y equals, and let's type this equation in. And let's graph it. And again, we see that kind of U shape there in the middle. Why is that? It's because we have those two vertical asymptotes there. So again, you can kind of see the rough shape of it, but let's see if we can get some of those middle points. So at 3, we have -3.5. At 7, we almost have 1. So again, plot as many points as you deem worthy. You know what's happening here though. So you can kind of use that one good point in your asymptote to get your rough sketch. Lots of fractions when we graph there. All right, you are done with 8.2 and 8.3. So your homework is on the new module guide that is waiting for you. You need to make sure to grab that. You also need to make sure to grab the worksheet because there's a worksheet for 8.3. So do you have bookwork from 8.2? Yes, worksheet is from 8.3. If you have any questions, please feel free to text me on Remind, or if you want to come in Tuesday morning, that is when I will have my office hours. But other than that, feel free to YouTube any other videos going over rational functions. There's a ton out there. But other than that, if you need me, just holler.